Imagine a warehouse the size of a city. Lights, conveyor belts, and shipping crates stacked to the ceiling. You are not allowed to walk the floor. You cannot touch a single machine. And yet, if one crate is in the wrong aisle, customers vanish. That is the problem Kubernetes was built to face. A living system of computers you cannot babysit by hand. Before a command line bridge existed, operators logged into machines one by one. They started containers like they were turning keys in a row of locked doors. One door left open, one version slightly wrong, and the whole building disagreed with itself. The stakes were not academic. A cluster that cannot be steered becomes a cluster that cannot be trusted. Tonight's story is about the thin tool that sits between a human intention and that warehouse of machines. Not a dashboard, not a wizard, a sentence you type that becomes an API request, that becomes coordinated reality. The question that opens everything else is simple, and it is not technical yet. How do you tell a city of computers what you want without shouting at every street? The answer the source gives has a short name, kubectl. It is a client-side tool, a bridge between a person and a Kubernetes cluster. You sit on one side with a keyboard, the cluster sits on the other with its own laws. kubectl is the translator in the middle. When you type a command, it authenticates with the cluster. It does not wander the worker machines itself. It sends a request to the API server, and that server coordinates with etcd, the controller manager, and the scheduler to execute your will. Think of it as a diplomatic cable, not a remote control car. You do not drive each node. You declare an intention, and the control plane argues it into existence. That distinction is the entire drama of this story. Imperative control says, go there, do this, now. Declarative control says, the world should look like this and keep looking like this. kubectl can do both, but its deepest power is the second kind. The cluster is not a pile of servers, it is a conversation. And kubectl is how a human joins that conversation without becoming one more moving part. Look at the master node, the control plane, as if it were a city hall. 4 rooms matter. The API server is the front desk. Every request that kubectl sends arrives here first. Nothing else is supposed to sneak in the side door. Below it, the controller manager is the department that never clocks out. It watches the recorded desire and the recorded reality, and it keeps trying to close the gap. The scheduler is the assignment clerk. A new pod is not a running process yet. It is a wish that still needs a physical desk. The scheduler chooses which worker node should host it, and etcde is the vault. It is the key value store that remembers cluster state. If the API server is the mouth, etcde is the memory. The source's architecture is blunt about the order. A user executes a command. Authentication happens against the master through the Kubernetes API server. Based on the type of request, that server orchestrates control manager, scheduler, and etcde. Without that front desk, kubectl would be a voice shouting into fog. With it, a typed line becomes a recorded fact. The cluster can disagree with you later. Machines fail, but it cannot pretend it never heard you. Now the other half of the map, worker nodes. These are the factory floors. Each worker in the source diagram carries the same 4 pieces. Kubelet is the floor supervisor. It talks to the API server and makes sure the containers that were assigned here actually exist. Kubeproxy handles the plumbing of network rules, so traffic can find a pod even when pods come and go like shifting stalls in a market. The container runtime is the engine that actually starts and stops containers. And the pod is the smallest unit you usually care about, 1 or more containers sharing a life. The diagram shows 2 workers, not 1, on purpose. A cluster is plural. If you SSH into a single machine and start a process, you have a pet. If the scheduler can place the same pod shape on either floor, you have cattle. kubectl never draws the pod by hand on a particular node in the happy path. It speaks to the API server. The API server speaks to kubelet across a dashed line of trust. The mystery for a new operator is always the same. I typed a command on my laptop. Why is something running on a machine I have never logged into? Because the worker is not waiting for you. It is waiting for the control plane. Follow one request as if it were a parcel. You type. kubectl authenticates. The parcel hits the API server. If the request is to store a new object, etcd writes it down. That writing is the moment intention becomes cluster law. Controllers notice the new law. A deployment controller, later in our story, will insist that a certain number of pods exist. The scheduler notices an unbound pod, a wish without a home, and binds it to a worker. Kubelet on that worker sees the bind, calls the container runtime, and a process begins. From the outside, it looks instantaneous. From the inside, it is a relay. Each hop can fail in a different dialect. Authentication can refuse you. The API can reject a bad object. The scheduler can find no node that fits. The runtime can fail to pull an image. kubectl's job is not to hide those failures forever. Its job is to be the honest messenger at the first hop. That is why the source insists on architecture before syntax. A command is not magic. It is a letter into a bureaucracy that actually works, most of the time, because every bureau has a single job. The tension we carry forward is this. If the letter is wrong, the bureaucracy will faithfully implement the wrong world. Before you can send that letter, the messenger has to exist on your machine. The source is practical here. You can install kubectl on Linux, on macOS, and on Windows. After install, you do not guess. You run kubectl version. The screenshot in the material is more honest than a brochure. Client version reports itself as one generation, server version reports another. A warning appears. The version difference between client and server exceeds the supported minor version skew. That warning is a character in this documentary. The cluster and the laptop are not the same organism. They age at different speeds. Operators live in that skew. The command still talks, but the conversation is slightly out of tune. Installation is not the climax. It is the moment you discover that kubectl is a client, not the cluster itself. You can hold a current client against an older server or the reverse, and the tool will complain in English. Cross-check, the source says. Run the version command. Read both sides. Only then do you trust the next sentence you type. A bridge that does not know which riverbank it stands on is not a bridge. It is a guess. Every kubectl sentence shares one skeleton. The source writes it as kubectl, then command, then type, then name, then flags. Command is the verb, create, get, describe, delete, apply. Type is the kind of Kubernetes object you are aiming at. Pod, namespace, deployment, service. The note is easy to skip and expensive to ignore. Type handling is case sensitive. Name is the particular object, like my-ngngx-pod. Flags are the optional modifiers, a namespace with -n or an output format with -o YAML. This is not poetry. It is a filing system that happens to be typed by humans. Get the order wrong and you are talking to the wrong clerk. Get the case wrong and the clerk claims the file does not exist. New operators often treat flags as decoration. They are not. -n is how you choose which room of the building you are in. Without it, you are in the default room, which may be empty even when your real work is thriving next door. The syntax is the grammar of power. Once you can hear a line as verb, noun, identity, and context, the rest of the tool stops feeling like a secret language and starts feeling like a very strict sentence. Kubernetes does not drop every object onto one infinite table. A resource is created inside a namespace, a named enclosure, so other resources can live in a separate environment. The source's first real act is not a pod, it is a room. You create a namespace, then you create a pod inside it. In the original walkthrough, the room is given a branded name. We will call the same idea a demo namespace, because the point is the wall, not the label. A namespace is not a virtual machine. It is closer to a labeled drawer. Objects in different drawers can share the cluster's blood supply, the nodes and the network, while keeping names from colliding. Two teams can both own a pod called web if they live in different drawers. That is the quiet political invention. Isolation without new hardware. The command is almost ceremonial. kubectl create namespace, then the name. After that, the cluster has a place that did not exist a second ago. Empty rooms are easy to forget. They are also easy to delete later, and when you delete the room, everything in it can vanish. Remember that cost. The story of creation is already rehearsing the story of erasure. A namespace is only a drawer. What you put inside it is the real bet. In this story, that bet is a pod, the smallest unit Kubernetes will actually run. You do not type the whole life of a container into a one-line command if you can help it. You write a file. YAML here is not decoration. It is a contract. API version v1, kind pod, then metadata that names the object, then a spec that names the container and the image it should pull. The image in the source walkthrough is nginx version 1.14.2. That is a web server in a box. You are not installing nginx by hand on a machine you can SSH into. You are asking the cluster to fetch that image and keep a process alive inside a pod. The file is applied or created with kubectl, pointing at a path. kubectl create -f, or later kubectl apply -f. The -f flag is the hinge. It says, do not invent this object from flags alone. Read the declaration. Watch what that declaration actually claims. API version and kind tell the API server which schema to use. Metadata.name is the identity you will later type in get and delete. The spec.containers list is the payload, a name for the container, and an image string the runtime must understand. If the YAML is wrong, a misspelled kind, a missing indent, the API server refuses the parcel before any worker node ever hears about it. That refusal is a gift. Better a validation error in your terminal than a half-running process on a machine you cannot see. Here is the part that matters. The file is desired state, not a script of steps. You are not saying, first download, then unpack, then start. You are saying, there should exist a pod with this shape. Kubernetes is then responsible for the how. That is why the same file can be reapplied later. The cluster compares what you wrote with what is live. If they already match, nothing dramatic happens. If they do not, controllers start moving. But a file sitting on disk is still only a wish. The next question is brutal and practical. After you hit enter, how do you know the pod is actually there and in the namespace you thought you used? You sent the parcel, now you have to ask whether anyone signed for it. The verb for that question is get. kubectl get pods with no extra flags looks in the default namespace. If you created your pod elsewhere, the default listing can look empty, a blank table that feels like failure. It is not always failure. It is often a drawer mistake. Add -n and the namespace name, and the same command suddenly shows a row, a pod name, a ready count, a status, a restart count, and age. Status running is the word you want. Pending means the scheduler or the image pull is still working. Crash loop backoff means the container started and died, over and over. The source walkthrough makes this contrast explicit. List without the namespace, see nothing useful. List with -n, see the pod you declared. The cluster did not lose your work. You asked the wrong room. Get is a census, not a biography. It is fast on purpose. Hundreds of pods can print as a table you can scan in a second. That speed is why operators live in get all day. You can get namespaces themselves. You can get deployments. The pattern is the same. Type, optional name, optional flags. Type is case sensitive, as the syntax page warned. Pods is not the same token as pods in every context, and a typo becomes a confusing error instead of a table. When the table says running, you still do not know which node accepted the work, what IP the pod received, or which events fired during the start. Those details hide behind a slower verb. So get answers the first honesty check. Does the object exist where I think it exists? The next honesty check is uglier. When something is almost running or running and still broken, you need the story, not the census. That story is describe. Describe is the verb you reach for when the table is not enough. kubectl describe pod with the name and the namespace dumps the biography. The source output is dense on purpose. You see the image, nginx 1.14.2, you see status, running, you see an IP address, the pod's own address inside the cluster network, not the public internet. You see which node accepted the work, then the conditions, 4 of them, like a checklist the control plane keeps ticking. Initialized, ready, containers ready, pod scheduled. When all 4 are true, the pod is not merely present. It has been placed, started, and declared ready to take traffic from the cluster's point of view. Events sit at the bottom of describe, and they are the closest thing this system has to a black box recorder. Pulled image, created container, started container, scheduled onto a node. If something failed, the event list is where the dialect of failure shows up. Failed mount, failed pull, failed scheduling. This is why describe is a troubleshooting tool, not a pretty printer. Get told you running. Describe tells you why it is allowed to say running, or why it is lying by omission, still restarting while the table looks calm. Notice the split of attention: the name, the namespace, the image, the node, the conditions, the events. None of that is in the YAML you wrote, not all of it. YAML is desire. Describe is reality plus history. If ready is false, you do not scale yet. You do not delete and panic either. You read the last events, then you decide whether the image tag is wrong, the node is full, or the probe is failing. The documentary beat is simple. A cluster that will not explain itself is a cluster you cannot trust. Describe is how kubectl forces the API server to narrate the object back to you. And once you can read that narration, you stop thinking in single pods. You start thinking in the verbs operators actually repeat all day. List, describe, scale, apply a service, delete. The popular set, the toolkit, not the museum piece. A craft is a handful of verbs you can do half asleep. The source collects them on one page, not as trivia, but as the working set. kubectl get pods -n, namespace name, the census we already used. Then kubectl describe deployment, because once you leave a single pod, the object you care about is often a deployment, a controller that owns replica pods. Then scale. kubectl scale with a type, a name, and a flag. Replicas equals some integer. That flag is not a suggestion. It is a new desired count. Controllers notice the difference and create or destroy pods until the live count matches. Then apply for a service. A service is how other things find your pods without memorizing pod IPs that change when pods die. kubectl apply -f, pointing at a service YAML, creates or updates that network identity. Then delete. kubectl delete pod, name, namespace. One object gone, or at least marked for deletion, while the API server and kubelet finish the funeral. These 5 moves are not 5 products. They are one grammar: command, type, name, flags. The same skeleton from the syntax page, reused until it becomes muscle memory. Scale is the emotional one, traffic spikes. You do not SSH into 10 machines. You change a number. The cluster either can place the extra pods or it cannot. And if it cannot, describe and events will tell you the node is full or the image will not pull. Apply is the quiet one. You keep the YAML and version control. The cluster is not a snowflake. It is a checkout of a file. Delete is the dangerous one, and we will give it a whole chapter. For now, notice that the popular list already assumes you know which namespace you're in. -n is not optional politeness. It is how you avoid editing the wrong city. The next object on the page after a lonely pod is the deployment YAML. Replicas set to 4, labels tying a selector to a template. That is where a single container becomes a small fleet. A pod is a person. A deployment is a hiring plan. The YAML on the source page makes that difference visible in a few fields. API version is apps/v1, not v1. Kind is deployment. Metadata.name is my deployment. Under spec, replicas is the number 4, not 1. 4 copies of the same idea. Then the selector, match labels app:myapp1. That is the hiring filter. The deployment claims every pod that wears that label. The template below stamps the same label on pods it creates, app:myapp1 again. If those two disagree, the controller is a manager who cannot recognize their own staff. Inside the template, a container named mycontainer1, image ngnx:latest. Latest is a moving tag. The source uses it anyway, as many tutorials do. In a real cluster, latest is a loaded word. It can change under you. For this walkthrough, it is simply the image string the runtime must pull. The selector and the template labels are the quiet architecture of replica sets. You do not have to type replica set yourself. The deployment creates one. The replica set creates pods. Your file stays at the deployment layer, which is the layer you scale and roll. 4 replicas means 4 pods if the cluster has room. The scheduler still places them one at a time onto nodes. Kubelet still pulls the image 4 times, or uses a cache. Kubeproxy still has to know how to reach whichever pods a service later selects. This is declarative control at a human scale. You did not write a loop, you wrote for. The control plane turns that integer into processes. kubectl apply -f on that file is how the hiring plan enters the API. Namespace can be in the YAML metadata or on the command line. Either way, the deployment lives in a drawer, and its pods live in the same drawer. The file is now the plan for a fleet. The next fight is not poetry. It is a practical collision. What happens if that object already exists and you try to create it again instead of applying it? Create and apply look like twins. They are not. The source shows the bruise. The first time, kubectl create -f on the deployment file works. The API server accepts a new object. The replica set appears. Pods start. Run create again on the same file and the cluster does not shrug. It errors. Already exists. Identity is unique inside a namespace. You cannot have 2 MyDeployment objects in the same drawer. Create means make a new one, and new is a one-time event. Apply is the other contract. Kubectl apply -f means make the live object match this file, whether the object is new or old. First time, it creates. Second time, it patches. That is why teams put apply in scripts and keep create for the rare greenfield moment. The walkthrough then changes the file. Replicas was 4, now it is 2. Apply again. The deployment's desired count drops. Controllers terminate extra pods until 2 remain. You can watch that with kubectl get deployments and kubectl get pods. The replica column moves. The pod list shortens. This is the documentary's central tension made small enough to hold. You did not SSH in and kill processes. You edited an integer. The cluster performed the violence for you, according to policy. Already exists is not a bug. It is the API protecting identity. If create silently replaced objects, a typo could wipe a fleet. The error forces you to choose. Did you mean a new name, a new namespace, or an update via apply? Get deployments after apply is the census for controllers. Ready and available columns tell you whether the live pods caught up to the new number. If they have not, you are back in describe. So the grammar gains a moral. Create is a birth certificate. Apply is a living will. Mix them up and the cluster will not guess your intent. When the will says the fleet should vanish entirely, even apply is the wrong tool. You need delete, and you need to know that deleting a drawer can take the furniture with it. Deletion looks like the inverse of create. It is more like demolition with a permit. kubectl delete pod. Type, name, namespace. The API server marks the object. Kubelet is told to stop containers. The pod disappears from get when the funeral is done. That is one grave carefully dug. Kubectl delete namespace is a different order of magnitude. The source is explicit. Deleting a namespace also deletes the resources inside it. The drawer does not empty politely and wait. The drawer is removed and the files go with it. That cascade is the feature you wanted when you use namespaces as blast radius walls. It is also the accident you get if you delete the wrong name. There is no separate "are you sure about the children" in the basic command the walkthrough shows. The namespace is the unit, so the operational discipline writes itself. Name namespaces like you name cities, not like you name temp files. Look with get before you delete. Remember that pods, deployments, and services in that namespace are in the blast. After a namespace delete, get pods -n, that name should fail or show nothing, because the room itself is gone. That is how you confirm demolition, not by staring at a node's file system. You can delete a deployment and leave the namespace. You can delete a pod and let a deployment create a replacement, which surprises people. If a controller still wants 4 replicas, killing one pod is a paper cut. The replica set grows a new one. To shrink the fleet, change replicas or delete the deployment. The source's pair of examples, delete the pod, then delete the namespace, is a sequence with a moral. First, remove a single workload. Then, remove the whole drawer and accept the cascade. This is still kubectl talking to the API server. No SSH, No walking the warehouse. The danger is not that the cluster will not obey, the danger is that it will. Once you can create, inspect, update, and destroy, the remaining question is not syntax, it is stamina. How do you live in this tool when you have many clusters, many namespaces, and a brain that cannot hold kubeconfig context in working memory all day? Syntax gets you in the door. Features keep you from drowning. The source names several, and they are not marketing fluff. They are how a CLI survives contact with a real job. Resource management, create, update, delete the objects we have been tracing. That is the obvious job, and it is still the job. Without it, kubectl is a flashlight with no battery. Cluster inspection and debugging, get, describe, logs, events. The ability to ask the API server what is true, not what you hope is true. A distributed system lies by being large. Inspection is how you refuse the lie. Context and multi-cluster management. Kubeconfig files hold clusters, users, and contexts. A context is a named triple. Which cluster, which user, which namespace. So one laptop can speak to staging and production without mixing the keys. Switch context and the same kubectl binary aims at a different city. That is power with a shadow. The command looks identical, the cluster is not. A scale or a delete in the wrong context is a documentary of a different kind, the incident kind. Extensibility sits beside those features. kubectl is not a closed box. It can grow verbs through plugins. The source points at that door because no vendor can predict every workflow. Together, these features answer the opening problem at human scale. You cannot walk every machine. You also cannot remember every cluster by IP address. Contexts name them. Inspection reads them. Resource commands change them. None of this removes the API server. It only makes the path from your fingers to that server less brittle. The next layer is the ecosystem around the binary. Plugin managers, context switchers, prompt widgets, and tools that are not kubectl at all. When the CLI is both essential and insufficient, people build furniture around it. No serious tool stays alone. The source closes by naming the companions. Crew is a plugin manager for kubectl. It installs extra verbs so the binary can grow without you compiling anything. The core stays small, the job gets specific. kubectx and kubens are the fast hands for context and namespace. Instead of editing kubeconfig like pros, you switch cluster or drawer with a short command. That speed is safety if it makes you look at the name, and danger if it makes switching too cheap to notice. kubeps1 puts the current context into your shell prompt. The documentary value is obvious. You should see which city you are about to demolish before you type delete. A prompt is a seatbelt, then the alternatives. K9s is a terminal UI that sits on the same API. You navigate pods with a keyboard instead of assembling get flags. Helm is a package manager for Kubernetes objects. Charts instead of one-off YAML files. Useful when an application is many deployments and services glued together. OC is the OpenShift CLI, a cousin for a particular Kubernetes distribution, with extra verbs for that world. None of these replace the API server. They change the cockpit. kubectl remains the reference grammar. Command, type, name, flags. The others are translations, overlays, or specialized dashboards. The source lists them after features for a reason. Once you understand the bridge, you are allowed to ask whether you want to stand on it in the rain or build a roof. Plugins and UIs are roofs. The road underneath is still HTTP to the API. If you only memorize tool names, you have not learned the cluster. If you only memorize kubectl and refuse every companion, you will type yourself into exhaustion. The honest middle is this: learn the grammar until create, get, describe, apply, scale, and delete are reflexes. Then let crew, kubectx, K9s, or Helm take the repetitive miles. Which brings us back to the warehouse you could not walk, and whether a typed sentence ever really steers a factory of machines. We opened in a warehouse you could not walk, machines you could not pet, a factory whose parts would drift if every human had to touch every node. Kubectl does not make the warehouse small. It makes the warehouse addressable. A command becomes an API request. The API server writes the desire into etcd, argues with controllers, consults the scheduler, and speaks to kubelets. Worker nodes run pods. Kube proxy stitches network. The container runtime keeps processes alive. You learned the grammar: command, type, name, flags. You learned that type and name are case sensitive because identity is not a vibe. You installed a client that can skew from the server, 1.6 versus 1.2.8 in the source screenshot, and still talk, with a warning. You put a namespace first, then a pod from YAML, then asked get whether the default drawer was the wrong drawer. You read describe until conditions and events felt like a black box tape. You scaled a number. You applied a service. You met already exists and understood why apply, not create, is the living will. You watched replicas move from 4 to 2 because a file changed. You deleted a pod, then a namespace, and accepted that drawers take their contents with them. You saw contexts, plugins, crew, kubectl text, kubeps1, K9s, Helm, and OC, not as a shopping list, but as proof that the bridge is load-bearing enough for a city to grow around it. The opening stakes resolve this far. You do not need to stand in every aisle. You need a faithful clerk at the front desk, a ledger that does not forget, and controllers that keep walking until reality matches the paper. The unresolved question is the one the field is still chasing. How much complexity can we keep hiding behind a declarative file before the file itself becomes another warehouse we cannot walk? When apply succeeds and the cluster is still wrong, the next mystery is not a missing flag. It is whether desired state was the right story to tell. Until that question is settled, the clerk remains. You type, the cluster answers, and the lights on the far machines either come up or they tell you in events why they will not.